Saxena. Please start the recording. Yeah. Dr. Aditya Saxena, presently working as assistant professor in the Department of Physics, Deshbandhu College, University of Delhi, with over about 16 years of experience in both teaching and research. He has published 20 research papers in international refereed journals and has presented papers in international and national conferences, and has been awarded the Best Innovations Award in 2015 by University of Delhi. He has been a member of numerous committees of UGC, ECEC, and other academic institutions, and has also been the head department of physics and dean school of physics and mathematical sciences at Central University of Haryana. So we all know him well, and he is progressing with us to deepen our understanding of statistical mechanics. It's a pleasure to have you, Dr. Aditya, with us. Please start sharing and kindly deliver your lecture. Thank you.
Thank you so much, ma'am, for such a wonderful introduction. So I'll start my lecture, and in fact, what I'll do is I'll start from some of the problems that I wanted to discuss yesterday but could not. So I'll start from there, and once I've done that, then I'll move on to what I was wanting to discuss today. So just I'll start sharing my screen. Is this visible? Is my screen visible now? Right. Okay. Okay. So, like I said, I was wanting to discuss some more problems regarding partition function, and this is another problem. So the problem is that for a system of two bosons, each of which can occupy any of the two energy levels 0 and epsilon, the mean energy of the system at temperature T with beta is equal to 1 by kBT is given by. So there are four options over here. Now we know that in case of bosons, since it's a two energy level system, so the bosons can occupy any of the two energies, right? So when both the bosons are in the ground state, right? So because there is no restriction on how many bosons can occupy a particular energy level, so when both the bosons are in the ground state, the total energy is 0. When one boson is in the ground state and one is in the excited state, then the total energy of the system is epsilon. And when both the bosons are in the excited state, then the total energy of the system is 2 epsilon. And both the energy levels are non-degenerate, okay? Because as is clear from the question that it is only saying two energy levels, one at 0 energy and the other at energy epsilon. And there are no further subdivisions in these energy levels, which may have constituted some kind of a degeneracy. So both the levels are non-degenerate. So using the partition function, we get, so for the first case, that is when both the bosons are in energy level 0. So this is e to the power 0 by kBT. So e to the power 0 by kBT is e to the power 0, which will give you 1. Then for the second case, you have e to the power minus epsilon by kBT, right? Because here the total energy of the system is epsilon. And for the third case, you have e to the power minus 2 epsilon by kBT, because now the total energy of the system is 2 epsilon. So this is your partition function for this situation. And the average energy, so the average energy would be basically multiplying the energy in each case with the partition function for that particular case. Okay, so 0 in one first case plus the energy in the second case is epsilon. So epsilon times e to the power minus epsilon by kBT. The third is the energy is 2 epsilon. So 2 epsilon times e to the power minus 2 epsilon by kBT upon the partition function. So the partition function is 1 plus e to the power minus epsilon by kBt plus e to the power minus 2 epsilon by kBt. So when you so you can just simplify this. So you get this e to the epsilon e to the power minus epsilon by kBt plus 2 epsilon e to the power minus 2 epsilon by kBt upon this. And this, if you see, is matching with okay, it's not matching with any of the options that they've given us. So as a result, you can say that none of the options basically correspond to this. So none of these options are actually matching. Okay, and now now we go to the next question. There are 4 energy levels, E, 2E. There are 4 energy levels, E, 2E, 3E, and 4E, where E is greater than 0. There are 2 particles and they are fermions. Then the canonical partition function of the 2 particles is given by. So now here, if you look at this, and these are the 4 options. So since they are fermions, see, like in the earlier case, I said that they were bosons. So you could have any number of bosons going into a single particle state. But in this case, because we have fermions, therefore, one state can at the max allow only one fermion, right? Because we know that the fermions follow the Pauli's exclusion principle. And because the fermions are following the Pauli's exclusion principle, therefore, only either that energy level remains empty or that energy level is occupied at the maximum by only one particle. Okay, so since there are 2 particles, so what can be the combination of energies, right, of the system? So in the first case, the first fermion occupies the energy. So the total energy of the system in that case would be 3E. In the second case, the fermion, let's say first fermion occupies energy E, second fermion occupies energy 3E. So in that case, the total energy of the system is 4E. Third case, now third case actually, so one fermion occupies energy E, the other fermion occupies energy 4E. So this becomes total of 5E. Now, fourth case is that one fermion occupies this energy, 2E, plus second fermion occupies energy 3E. So this also becomes 5E. So basically, this case, E is equal to 5E will occur twice for 2 different configurations. In one case, one fermion occupies energy E and the other occupies energy 4E. In the other case, one fermion occupies energy 2E and the other fermion occupies energy 3E. So there are 2 different configurations for this. So here you see that you have, because there are 2 different configurations occurring for this. Then if you move further, what you have is, so this basically, this level has a degeneracy because 2 different configurations correspond to the same energy. So there is degeneracy in the level E3. Then we move on to the next. So one fermion occupies 2E, the other fermion occupies energy 4E. So this is level 6E. Then in the third case, one fermion occupies energy 3E and the other fermion occupies energy 4E. So that energy is total 7E. So now if you want to write down the partition function, so Z is, so for the first case, it will be Z is e to the power minus 3E by kBt. For the second case, e to the power minus 4E by kBt. For the third case, because it's a doubly degenerate state, there are 2 different configurations which have or which correspond to the same energy. So this is a doubly degenerate state. So GI in all the other cases, the GI was coming out to be 1. but in this case, the GI is 2. So here twice e to the power minus 5e by kBt plus e to the power minus 6e by kBt plus e to the power minus 7e by kBt. So you see in all these other levels, there is no degeneracy, but in this level, since the degeneracy is 2, therefore you multiply this factor by 2. So your answer, if you look at these options, then this is your correct answer, C. Okay, now if you look at the same question, but now we have changed the particles. Now the particles that we are considering are distinguishable. So when I say that the particles that we are considering are distinguishable, what do I mean? That now the particles are classical particles. We do not need to bother about the spin, number one. Number two, that they are, any number of these particles can be put in any one energy state, all right? But supposing if I put one particle in energy E and the other particle in energy 2E, and so let's say there are two particles which are distinguishable. So let me label them as particle A and particle B. So if I put particle A in energy E and particle B in energy 2E, that constitutes one configuration, okay, or one system. Now if I interchange the particles, so this configuration that particle A is energy E and particle B is in energy 2E, this configuration has a total energy of 3E. Now if I interchange the particle, my configuration has changed because the particles are distinguishable. So now particle B goes to energy E and particle A comes to energy 2E. So now this is another configuration which is different from the earlier one, but still the total energy is 3E, okay? So the total energy remains 3E. So what we see from this is that if both the particles are occupying energy E, then the total energy of this configuration is 2E. If both the particles occupy energy 2E, then the total energy of the system is 4E. If both the particles occupy energy 3E, then the total energy of the system is 6E. And when both the particles occupy energy 4E, then the total energy of the system is 8E. And you have intermediate energies also. When one particle occupies energy E and the other 2E, so total energy becomes 3E. Similarly, when one particle occupies energy 2E and the other 3E, then total energy becomes 5E. Similarly over here, that when one particle occupies energy 3E and the other particle occupies energy 4E, so 3 plus 4 is 7E. So in this manner, what you are seeing is that the energy levels 3E, okay, 3E, 5E, 7E are doubly degenerate energy levels, okay? And the energy levels 2E, 4E, 6E, and 8E are non-degenerate energy levels, right? Because the energy levels 3E, 5E, and 7E, there are two different distinct configurations corresponding to the same energy. So they are doubly degenerate, okay? And now when you, so you solve this, so basically you can simplify this and you finally get e to the power minus epsilon by kBt plus e to the power minus 2 epsilon by kBt plus e to the power minus 3 epsilon by kBt plus e to the power minus 4e by kBt and this whole square. So this will give you your total partition function and this corresponds to the option D. So this is another equation that I wanted to discuss with you. Next is a problem. This is regarding calculating, these some of the thermodynamic quantities. So you have a collection of n two-level systems with energy 0 and E, which is greater than 0, is in thermal equilibrium at temperature T. For T tending to 0, the specific heat approaches 2. So first of all, for this system, we find out the partition function, all right? So you have a collection of n two-level systems, okay? So n two-level systems, and the two levels are 0 and E. So your partition function becomes e to the power minus beta times 0 plus e to the power minus beta beta, you know, is 1 by kBt. Okay, so e to the power minus beta times 0 plus e to the power minus beta times e. So this gives you 1 plus e to the power minus beta e, right? And then if I take the log of the partition function, so log of 1 plus e to the power minus beta e. Now the internal energy E is simply the expectation value of E. So e to the power minus, and you, this is the formula. So e minus del by del beta times log of the partition function. So del by del beta times log of 1 plus e to the power minus beta E. So you do the differentiation. This is what you get. Then since specific heat is del U by del T at constant volume, okay, U was the internal energy, so we calculated the internal energy, and specific heat at constant volume. So this is del U by del T at constant volume V. And so you do this differentiation. So now you replace this beta by 1 by kBt. So this is the expression that you get. You do this differentiation, solve it. So finally what you get is Cv is e square by kBt square e to the power minus e by kBt upon 1 plus e to the power minus e by kBt, and this whole square. And so now when you look at this expression, now what they are saying is, as t approaches infinity, all right? So as t approaches infinity, this goes to infinity, e to the power 0 is 1. This also, this approaches infinity, so e to the power 0 is 1. Here there is t in the denominator, so if this t goes to infinity, this term goes to 0. So this whole thing goes to 0. So Cv at t tending to infinity, Cv is 0, so your answer is A. Okay, so this was another example that I wanted to discuss with you. And so this was some of the other numericals that I wanted to do from last time. And now I'll come on to what I was wanting to discuss today. So I'll again share my screen. I'll now take the other presentation. Okay.
Yes.
All
Yes.
right.
Now it
So
is visible.
now the next thing that I wanted to discuss with you people is the Bose Einstein and the Fermi Dirac gases and their applications. So we have already in the past two sessions that we have been discussing Maxwell-Boltzmann statistics, Bose-Einstein statistics, and Fermi-Dirac statistics. And we have done that discussion in detail. We have discussed their partition functions. We have discussed their distribution functions. We have discussed their various properties. We have discussed how the particles will stack up the different energy levels for all the three statistics. So having done all of that discussion, now we finally come on to the Bose-Einstein gas and the Fermi Dirac gas. Okay, so before I go on to discussing the Bose Einstein gas and the Fermi Dirac gas, I would just like to do a recap, because this will also act as our starting point for today's discussion. So I would like to do a recap where if you look at this expression was the Bose-Einstein distribution function. We have already been discussing this in the previous two sessions. Now, if you where Ni is your the Bose-Einstein distribution function, right? And Gi was your degeneracy, okay? or the number of sub energy level that might be there corresponding to the same energy level. So, and epsilon I was the energy of that ith level, mu was the chemical potential, Kb was the Boltzmann constant, and T is obviously the temperature at which we are looking at the system. And so this was the distribution function. Now, if I do a slight tinkering in the distribution function, then I can rewrite this distribution function as Gi upon Ni plus 1 is equal to e to the power epsilon I minus mu by kBt. All right. So basically, I have brought Ni over here, and I've taken this quantity over there, and minus 1 I have brought over here. So this you get like this. Doing a similar thing for Fermi Dirac distribution. This is the Fermi Dirac distribution function. Again, you are familiar with this. We have been discussing this. Now, again, I'll do the same rearranging of terms. So Gi upon Ni minus 1 is equal to e to the power epsilon I minus mu by kBt. So you see that over here it was Gi upon Ni plus 1. Here it is Gi upon Ni minus 1. And if I look at the Maxwell-Boltzmann distribution function, which was this, okay, then this is again something that we've been discussing. So if I look at this Maxwell-Boltzmann distribution function, then and again rearranging the terms, so Gi upon Ni is e to the power epsilon I minus mu by kBt. Now, if this term Gi upon Ni, if this term becomes very large, okay, please, now this is something very important. So please pay attention to this concept, because this is something which is actually now going to be used in developing our theory for the Bose Einstein and the Fermi Dirac gas. So if this quantity, this Gi upon Ni is very large. So when I'm saying it, this is very large, what do I mean? I mean that Gi upon Ni is much, much greater than 1. Okay. So if my Gi upon Ni is much, much greater than 1, then this 1 can be neglected. Right? If in the Fermi Dirac distribution function, if this Gi upon Ni is much, much greater than 1, right? This is much, much greater than, then this minus 1 can also be neglected. So what this means is that if my Gi upon Ni is 1, then this plus 1 and minus 1, this plus 1 that is occurring in function, and this minus 1 occurring in the Fermi Dirac become negligible, right? And you can approximate this entire term Gi upon Ni plus 1 as Gi upon Ni only for the Bose Einstein distribution function. Similarly, you can approximate this Gi upon Ni minus 1 term as Gi upon Ni for the Fermi Dirac distribution function. So what does it tell us? It tells us that the if this is very large, if this is very large and you're neglecting this plus 1 or minus 1 terms over here, then these two simply reduce to or simply approach the Maxwell-Boltzmann distribution function, Gi upon Ni, because here you're neglecting the plus 1 because Gi upon Ni is very large. Here you're neglecting the minus 1 because Gi upon Ni is very large. And if you neglect this, so both these expressions, the expression for Bose-Einstein distribution function and the expression for Fermi Dirac distribution function, both of these expressions approach the expression for the Maxwell-Boltzmann distribution function. Now, what is the significance? In case of Bose-Einstein distribution function, Ni maybe could be greater than Gi, it could be less than Gi. Okay. And the reason for that is because any number of bosons can be put in a single sub energy level or in a substate. Okay. So here this Ni could be greater than Gi. So obviously when we are saying that Gi is much, much greater than Ni, So when would this thing be? Now, please, this is a conceptual uh, uh, point. So please pay attention to this. Uh, GI is your number of degenerate states or the number of energy levels that are available, sub-energy levels that are available that correspond to the same energy. All right. And Ni is your number of particles that are occupying that state. So basically what this means is when I say that GI is much, much greater than Ni, then what does it mean? Either my number of particles or the number density is very small, okay? In other words, my particles are very far apart and each particle has a number of energy levels which it can access or which it can occupy. So because each particle has, so what I'm saying is that the population of the energy levels or the sub levels that are available to the particles is much more than the population of the particles themselves. Okay. And this case typically happens at high temperatures. I'm not saying very high temperatures. When I say high temperature, what I mean is room temperature, typically room temperature. Otherwise, obviously high temperature, one also needs to take into account the kind of system that one is considering. So that is also important. So basically two things that are very important over here. One is your temperature and the other is your number density. Okay. So if you can all recollect from the first session, I had said that there are two conditions for the quantum effects to become significant. One condition is that my n lambda thermal cube, okay, where n is my number density and lambda thermal cube is the cube of the thermal de Broglie wavelength. So n lambda thermal cube is greater than 1. Sorry, is greater than 1. N lambda thermal cube is greater than 1. Okay. This is one important condition for the quantum effects to become significant. The other important condition for the quantum effects to become significant was that the thermal de Broglie wavelength, that is lambda thermal, is greater than or equal to the interparticle separation, which was 2Rs. Okay. So if these two conditions are satisfied, then you will realize that GI upon Ni will not be a very large quantity. Okay. It will not be a very large quantity. In fact, for bosons, it might be a quantity which may be less than 1. And this is something that we will see. Please remember this point carefully, because when we will talk about the Bose Einstein condensation, then we will specifically look at this aspect once again. So GI upon Ni, if these two conditions are satisfied, that is your lambda thermal is greater than or equal to the interparticle separation, and the product of the number density and the thermal cube of the thermal de Broglie wavelength is greater than 1, then quantum effects become significant. But if the thermal de Broglie wavelength is much, much less than the interparticle separation. Now, when I am saying the thermal de Broglie wavelength is much, much less than the interparticle separation, what do I mean? Now, like I had mentioned to you earlier, that the thermal de Broglie wavelength basically gives us an approximation of the extent, spatial extent in which the particle is likely to be found. Okay, or rather within which you can say that the probability of finding the particle is 1. So the thermal de Broglie wavelength gives us that extent. And if this is much, much smaller than the interparticle separation, that means the distance between two particles, then in that case, we know that the particles are very far apart. Second thing, that the number density times the cube of the thermal de Broglie wavelength, if this is much, much less than 1, or if this is less than 1, then what we are trying to say is that the volume available, okay, the phase space volume available to the particles is, to each individual particle, is much larger than the volume that that particle will occupy. So when I joined this session, Punita ma'am was just concluding her lecture. So she was talking about this phase space only, that 3 position coordinates and 3 momentum coordinates. So typically the volume that a particle would require in phase space, okay, if you are looking at it from the quantum mechanical point of view, then that volume is indicated or is signified or is depicted by the cube of the Planck's constant, okay, h cube. This is the phase space volume that a single uh, quantum state requires. Okay, so this is the phase space volume. So if your the volume that you have is much larger, then obviously the particle will only require this much volume, and hence uh, the particles they will have a much larger volume available to them than their own volume. Okay, so if these two are the points, then you will see that this gi upon ni, this ratio, is very large. All right. Now, in case of Bose Einstein distribution, now in case of Fermi Dirac distribution, we already know that gi has to be greater than ni, right? If you will recollect again, in the previous session, we had discussed this point that gi needs to be much greater than ni, not much greater than, but definitely greater than ni. Why? Because each gi can either be empty or can at the maximum accommodate only one particle, right? So if there are ni particles in the ith energy state having an energy epsilon I, and gi are the number of sub energy levels or substates that are present or corresponding to this energy epsilon I, then because the fermions follow Pauli's exclusion principle, therefore gi can either be empty, okay, any particular sub energy level or substate can either be empty, or it can at the maximum have only one particle, one fermion occupying it. So gi by ni in case of fermions, because of the fact that fermions follow Pauli's exclusion principle, is in any case greater than 1. Okay, but still it may be very close to 1. So when this ratio becomes very large, so this ratio will become very large again, like the same discussion I did for the Bose-Einstein distribution function, that when you look at the quantum conditions. So same discussion holds true over here also. So when this becomes very large, then both these distribution functions will approach the Maxwell-Boltzmann distribution function. And correspondingly, all the results will also approach the results of the Maxwell-Boltzmann distribution function. This is something which is very interesting. And so this is a very conceptual point that I wanted to discuss with all of you. Uh, so I hope that this is clear, and we will in any case be taking up this point in greater detail in the coming slides. All right. So now let me go on to the next slide. Okay. Now this is, although black body radiation we typically take up in the radiation theory, but I don't know how many of you are aware of this or not. Okay, I'll just give you this very, very brief historical context to this entire thing. In fact, this entire Bose-Einstein statistics. So the historical background um, or context to all of this is that how did it all start? This who's the Indian physicist whose name is associated in this Bose-Einstein. Bose comes first and the name of Einstein comes later. So Satyendranath Bose, he was a young man of, I think, some 20 to 23 years old. And he, so what he did was that he was looking at the Planck's distribution function, the Planck's Planck's radiation law. So Planck had obviously done a version of that to deduce his Planck's distribution function and the Planck's distribution law for black body radiation. So what Satyanath Bose did was that he did the same calculation using statistical arguments. Okay, so what were the statistical arguments that he used? He said that photons are particles of zero rest mass. So basically he looked at photons as particles. So obviously black body radiation is a collection of a huge number of photons. So he basically tried to look at that problem from the statistical point of view. So what he said was that photons are particles of zero rest mass, and secondly that they are identical and indistinguishable, but their number is not conserved. And this is because of the zero rest mass, because they have zero rest mass, and also because their chemical potential is zero, their number is not conserved. Okay, so basically what that means is that as the black body radiation is absorbed or emitted, the number of photons inside that black body so as to maintain that. So so the total energy, so you see, if you look at this, if you recollect in the earlier derivations, when we were looking at the Bose Einstein statistics and the Fermi Dirac statistics, there we had put two conditions. One was that the total number of particles is conserved, and second was that the total energy is conserved. But here what Bose argued was that only the total energy is conserved, the total number of particles are not conserved, because photons are quasi-particles having zero rest mass, and they are, now we call them as bosons, but what he said at that point in time was that they are particles of spin 1. All photons have spin 1. So he said that because they have spin 1, that is an integral spin, so they need not follow the Pauli's exclusion principle. So you can populate any number of photons in any energy state, right? So he gave this concept, and he did the statistical, using these statistical arguments, he derived the distribution function. So he got this expression for the number density, right? Where G nu is 8 pi V by mu square by C cube, and epsilon is H mu. So epsilon is the energy, total energy, mu is the frequency with which the photons are getting emitted or getting absorbed, right? And G mu is the, again, the degeneracy or the of that particular energy level. So he got this relation, and if you look at this relation, there is one thing very important over here, and which is that here the mu is not there. We have been looking at relations which had e to the power epsilon minus mu by kBt. Here that minus mu term is missing, and the reason for that is that because the particle number is not conserved, this can only happen if the chemical potential is zero. So yesterday there was a question in the question box where somebody had asked that what is the physical significance of the chemical potential. So chemical potential, I had although discussed this in detail yesterday also, but again I'll just do a brief recap. Chemical potential tells us the basically it gives us the energy that is required to put a particle in a state, right? Or the energy that will be freed up if we take out a particle from a state. So that is the significance of chemical potential. But because here the number is not conserved, so when you say that the number is not conserved, that means the photons can get created and annihilated, right? So because of that, the chemical potential is zero. So this was the work that Satyanath Bose did. He was a young man, and what he did was that he obviously tried to get that work published, but nobody, I mean, being an Indian, and this is I'm talking about 1922. So India was still under the rule of the Britishers, and being an Indian, so nobody really cared about his work. So then finally he sent his work to Einstein. And Einstein immediately realized the brilliance of this work, and he translated that work into German and got Bose's work published in a German journal, scientific journal. And then, but because Einstein realized the brilliance of this work, so then what Einstein did was that he developed Bose's work to include particles, or rather to include particles which have a zero or integral spin. So basically particles which do not follow Pauli's exclusion principle, but which have a finite mass. So this condition that the particles have zero rest mass gets changed. The particles have finite mass, and hence their number is conserved. So then that mu term also comes. So that was the contribution of Einstein, and that's why this distribution law is called the, I mean, this statistics is now called as the Bose Einstein statistics. And to honor the significant contribution that Bose made to this, in fact, it was his work originally, which then Einstein developed upon to include particles which had finite zero rest mass and whose number is also conserved. So then that's how it came about. Anyway, so coming back to this, so E mu d mu, this is the energy. So E mu d mu is dN by V h mu, right? This is the energy density. This is the energy density in the frequency range lying between mu and mu plus d mu. So this is given by, so dN was your number of photons in the frequency range mu and d mu, mu and mu plus d mu. This is the energy density. So basically dN by V gives you the density of photons lying in the frequency range mu and mu plus d mu, and then multiplied by the energy of the level epsilon, which is h mu. So you simply put this value over here, and what you get is this expression. So this is if you're looking at it from the perspective of a space which has, I mean, where we are considering the frequency as the coordinate. And if you look at, so when I say frequency as a coordinate, I've specifically written these two relations, and there is a reason for that. When I say d mu, so basically what I'm talking about is the energy space, right? Because energy is h mu. So, and h is a constant. So if you talk of the mu space, that is the frequency space, simply multiplying that space by this Planck's constant, you will get your energy space, right? The other relation I have derived is the same relation, but in terms of the lambda. This is the wavelength. So so the wavelength of the particle lying between lambda and lambda plus d lambda. This is the energy density for the photons lying between the wavelength lambda and lambda plus d lambda. Here, what am I talking about? You see lambda again. Lambda, if you look at the de Broglie's relation, right? So lambda is h by p, okay, and lambda is h by p, or you can write p is h by lambda. So if you are representing something in terms of the wavelength, then you can simply convert it into your momentum space. You can simply convert it into your momentum space by dividing, rather by inverting the wavelength space and then multiplying it by your Planck's constant. So in this manner, what you see is that that is why the significance of these two relations. So anyway, so these were the relations that you get for black body radiation using statistical arguments. And these relations obviously correspond exactly to the relations which Planck had derived. So these relations that I've written over here using these arguments were derived by Bose. Okay, now coming on to the Bose Einstein gas. So again, this is the familiar expression of the Bose Einstein distribution function. Now here there is one thing. When we are talking of a Bose Einstein gas, that means it is a collection of particles. So the number of particles in any state, okay, if the particle exists over there, it can, so either that state can be empty, in which case Ni can be 0, or that state will have some particles in which Ni will be greater than 0. So basically what that means is that Ni can never be less than 0. Now this is something which is very important. Either that state is empty, in which case Ni is 0, or that state has some population of bosons, in which case Ni is greater than 0. Okay. So now this condition, since we have this condition, therefore, now let us look at this denominator over here. This denominator has this expression -1. All right. So for this condition to be satisfied, that Ni has to be greater than or equal to 0. One thing that is very important is that the denominator should not be negative. All right. This denominator should not become negative, because if this becomes negative, then Ni becomes negative. And that from this condition, we know it cannot be. See, either a state can be empty or it will have some particles. So Ni being negative is physically untenable, right? It is not possible. So this denominator can never be less than 0. In other words, e to the power epsilon I minus mu by kBt has to be greater than or equal to 1, right? Now, if I say that for the ground state, my energy epsilon I is 0, that is, I'm putting this as equal to 0, then this expression reduces to e to the, this expression reduces to e to the power minus mu by kBt is greater than or equal to 1. And from this, you can say that the mu, this chemical potential, is less than or equal to 0. Yesterday, again, somebody was asking me how these chemical potentials vary. So I said that we will be taking it up in greater detail in the tomorrow session. So now you can see this. The chemical potential mu is less than or equal to 0. So that what that means is that for a Bose Einstein gas, the chemical potential will always be less than 0, which means it will be negative, and its limiting value will be 0, right? The limiting value of the chemical potential will be 0, otherwise it will be negative. Okay, now so again we write this GP/dP, right? So this GI, if you remember yesterday also I had mentioned this, that the GI can be when you are moving from when you're changing from these sub levels to the momentum state or the wave number. So you go from summation over I to summation over K. And if you remember when I said that when you go from summation over I to summation over K, then your GI becomes 1 and you have a summation over K. So when you go and when you now reduce the K space very small so that you're wanting to integrate it, then you get GP/dP is 4 pi p square dP by h cube by V. So what is this? 4 pi p square dP is your, if you have momentum between P and P plus dP, then 4 pi p square dP is your volume element in the momentum space lying between momentum P and P plus dP. All right. And V, okay. So V is the volume of the coordinate space. So V, so basically if you look at this expression, the V will come in the numerator, okay. So it is V times 4 pi p square dP. So this is the total volume in the phase space, because this is the volume in the momentum space. This 4 pi p square dP is the volume in momentum space of a volume element lying between momentum P and dP, right? It's like a spherical shell, okay? And V is the volume element or the volume in normal coordinate space. And what is this H cube? Like I just mentioned to you a little while earlier, that this H cube, is your minimum volume in phase space. You cannot have a volume element in phase space smaller than H cube. Why? Please recollect that the Heisenberg's uncertainty principle says delta x, delta px should be greater than or equal to h cross by 2, right? So delta x represents some finite extension in spatial coordinates. Delta px represents some finite extension in the momentum coordinates, right? So if I take delta x times delta y times delta z, that will become delta v, which is the volume element in the coordinate space. And similarly, if I take delta px times delta py times delta pz, that becomes the volume element in momentum space. So delta px times delta py times delta pz, if you convert that into a spherical polar coordinate system, then it becomes 4 pi p square dp. That dx times dy times dz is my volume dv, which I've integrated. So I get v, and on the right hand side, this volume element will always be greater than, or maximum it can be equal to, h cross by 2. So basically that h cross by 2 gives me that limiting value of the volume element that you can have in phase space. H cross q by 8 it will become, okay, h cross by 2 is delta x delta px, so h cross q by 8. So this is that minimum limiting value of the volume element that you will have in phase space. So that's why we've divided by h cube, because this is what is going to give you your number. What is this number? I said gp dp. So what is this number? The total volume in phase space, the total volume element in phase space that is available to you for accommodating the various particles, divided by the volume element, the unit volume element of phase space. So h cube gives you that unit volume element of phase space. So when you divide the total volume element in phase space by the unit volume element of phase space, then you get the total number of states, total number of accessible states in the phase space. So GPdP is the total number of accessible states in the phase space. And so now we substitute this. So DN lying between momentum P and P plus dP. So the total number of bosons lying between momentum P and P plus dP is given by this expression dNP, and this is simply Gp dP times this, okay, the Bose Einstein distribution function. So 4 pi V by h cube times P square dP. So this is coming from Gp dP, and this times this distribution function. So okay, so e to the power alpha plus this epsilon will take the value of p squared by 2m, because we are talking in terms of the momentum. So you know that energy is p squared by 2m. So alpha plus p squared by 2m by kBt, p squared by 2m kBt, and minus 1. So then if you now convert this into the energy coordinates, that is epsilon. So you know epsilon is p squared by 2m. Do that mathematics. I have now skipped that entire mathematics, so to that, but what you finally get is this relation, okay, v by h cube 2 pi m kBt whole to the power 3 by 2 f1 alpha, and f1 alpha is this integral that you get, because like I mentioned over here, you have an integral over here. So you integrate this entire thing and you do these conversions. So for example, p will be under root 2 m epsilon, okay, and dP will be so half m epsilon to the power minus half d epsilon, right? So in this manner, you can do that conversion. It's not very difficult. So doing that conversion, you finally get this expression where x is epsilon by kBt. So dx will become d epsilon by kBt, okay? So I have tried to do a double this thing, that I've not only converted the coordinates from p to epsilon, but I've done a further substitution. I've put epsilon by kBt as x and then done this. So finally, this f1 alpha is 2 by under root pi integration from 0 to infinity x to the power half dx e to the power alpha plus x minus 1. E to the power alpha plus x is simply this term, right? E to the power alpha plus x minus 1 is simply this term. Okay, so you do all of this mathematics. So what you get? You then finally get this expression for the total number of particles that are there. All right, the total number of particles that are there in the Bose Einstein gas. So this expression comes out to be v by h cube 2 pi m kBt whole to the power 3 by 2. R is equal to 1 to infinity z to the power r by r to the power 3 by 2, where z, okay, so f1 alpha was this, that we got from the previous slide also this. And now what I've done is that this approximates to summation over r going from 1 to infinity z to the power r by r to the power 3 by 2 for z less than 1. And what is z? If you can recollect from our last session's discussion, z was the fugacity factor. All right. So z was e to the power minus alpha. Okay. So z was e to the power minus alpha. So basically, what this term e to the power alpha is 1 upon z. Okay. This term e to the power alpha is 1 upon z, and this is your fugacity factor. So you can approximate this for z less than 1. And why we are saying that z is less than 1? Again, this is coming from this condition, right? So this is 1 upon z. So 1 upon z is greater than equal to 1. So basically z is less than equal to 1. So when I'm specifically taking the case for which z is less than 1, then this, you can approximate this relation as this. And so z to the power by r to the power 3 by 2, right? And then you look at the energy expression. So I'll just, I think, just take 1 minute. There is some, the screen I think has got stuck up. My presentation is not moving. So I'll just take 1 minute to sort it out. Just a minute.
Yeah, yes, sir.
Hello?
Yes, ma'am.
Yeah, ma'am. It is stuck for a second, so sir is reloading
Yeah,
again.
no
Yeah,
problem. No
I'll
problem.
just take 1 minute.
It doesn't matter. So students, again announcement for you. You have asked for books for where multiple choice questions are available. You see, the books which teach us statistical mechanics are the ones which I've mentioned in my ladder slide as well as in the list slide. All books are included. These books which are teaching you statistical mechanics in depth will not carry such type of questions. However, you can look for some books and compilations which are made for this purpose. And we can suggest one or two to you on the WhatsApp group, number one. Number two, Dr. Aditya will tell you which book he is following. I told you I have followed Beiser and Huang, right? And both the books are there in your WhatsApp. You can follow them. And in the coming week, we might have lectures of nuclear physics along with statistical mechanics. So you should work in resonance while statistical mechanics is going on. You should read during the day the basic books which we are referring to again and again. Read the chapter, come for the lecture, and then again ask for the following chapters of those books and then read them. So your concepts would be clear. You can give questions on email also. We'll try to answer them to the best of our possibility and capability. Additionally, if there are certain concepts of nuclear physics that you would like to clarify, then you can submit them through a Google form, which we will put up on the WhatsApp group. So you tell me what topics in nuclear physics are unclear to you, or if you have some specific questions, you can frame your questions in advance also. This is also the request by the group of electronics teachers who will be coming and meeting you after a few weeks, a whole week of electronics. So you can compile your questions and doubts and the concepts on which you would want more clarity, repeated explanation, etc. for electronics also. You can start doing it for all the subjects except classical and EMT, because those two subjects are now over. I hope I'm clear. Yeah, he's back. Dr. Aditya is back. Yes, yes, Dr. Aditya, please continue.
Yes, ma'am.
Sorry.
Thank you so much, ma'am. Okay, so like I said that if you look at this expression, right? So you look at this expression. So this is your n, and this is your expression for n. So now, so the expression for energy is epsilon times d and epsilon, right? And integrate it over all the energy states. So this is the final expression that you get for the energy, where F2 alpha is this integral. So again, I've done the same substitution that I'd done earlier, using the same substitution that x is e to the power x is equal to epsilon by kbt and dx is d epsilon by kbt. So doing the same substitution, I get this expression. And for F2 alpha, this is the expression. Again, this is the result that you get when you take z less than 1, all right, where z is your fugacity factor, that is e to the power minus alpha. So if you look at this expression, this e to the power alpha is 1 by z, all right. So your final expression for e turns out to be this. And when you solve this, so this expression okay, this when you take a ratio of e by n, and then you take n on this side, so e turns actually that n, I'm sorry that n has got missed out. So e is equal to 3 by 2 n kbt times 1 minus z upon to the power 3 by 2 minus z upon this, right? And if you look at there is an n also over here, so this is a typo error. 1 minus z upon 2 to the power 3 by 2 minus z upon 3 to the power 3 by 2. Now, like what I had mentioned to you, see, we have taken z to be less than 1. All right. Now, the limiting value of z is 1. Z can be less than or equal to 1. So when you take the limiting value of z that is equal to 1, when you take the other extreme of the z, because z is less than equal to 1. So when you take z as equal to 0, okay, when you take z is equal to 0, so then this equation reduces to E is equal to 3 by 2 n kbt. And now, okay, although we'll take this up slightly later, but I would want you to think about it, that when would z be equal to 0? Okay, z, like I said, is the fugacity factor, e to the so e to the power minus alpha is z. So when would z be equal to 0? So when z is equal to 0, this equation reduces to 3 by 2 n kbt. And like you can recollect, this is the expression that you get for the energy when you use the classical statistics, that is the Maxwell-Boltzmann statistics. So half kbt is the energy that you get from 1 degree of freedom. If there are 3 degrees of freedom for a 3-dimensional space, the total energy that you get is 3 by 2 kbt. And if there are n particles in the system, then 3 by 2 n kbt. So this expression reduces to that expression when your z becomes equal to 0. Okay. All right. So now coming to the another important concept in Bose Einstein statistics, and that is, or rather in the Bose Einstein gas, and that is your degeneracy of the Bose Einstein gas and Bose Einstein condensation. So please again refer to the discussion that I did with you at the beginning of this session, where I said that the onset of quantum mechanics, or when the quantum considerations become significant, the quantum mechanics or the quantum statistics becomes significant, is when your n lambda thermal cube becomes greater than equal to 1, and when your lambda thermal is greater than the interparticle separation, greater than or equal to the interparticle separation, right? So when this happens, then what is it? What actually when okay, these two conditions are looking like very mathematical, But what is the physical significance of these two conditions? The physical significance of these two conditions is that when we say that the wavelength, okay, the thermal de Broglie wavelength of a boson becomes so large that one single wavelength overlaps over at least two bosons, and maybe it may be overlapping over many bosons. So you have the waves of different bosons overlapping over one another, because one wavelength would extend way beyond that very boson and would also extend over a number of other bosons, right? What does this mean? That because the wavelength defines the extent in which the probability of finding the particle would be 1, right? So if one single wavelength is extending over many bosons, that means that in that extension there may be a number of bosons which might be present. Okay, that is what we mean by the wavelengths of different bosons overlapping. So in that, if you take any one particular extent or any one particular wavelength associated with any one particular boson, then probably that extent may have more than one bosons present, because there are other bosons also which are coming in that region. Okay, that's why the wavelengths are overlapping. So what happens is that now the bosons start, they would like to occupy. So more and more bosons start occupying one single energy level. All right. This is because the number of energy levels that are now available to the bosons, that number of energy levels is small and the number of bosons is large. So more and more bosons try to condense into one energy level, right? And this is what is called a degenerate boson gas. That when you have a number of bosons going into the same energy level, so this is what you call as the degeneracy of states. Okay, so you have so same energy, and again, so same energy, you may have sub energy levels in that. So these sub energy levels may be occupied by different bosons, and all of them will correspond to the same energy, same main energy level. So this is the onset of degeneracy. And how does this happen? Again, let's look at this factor, the fugacity factor, Z. So e to the power, Z is e to the power minus alpha. If you look at this expression, okay, if you look at this expression, so from this expression, you can rework this, okay, and you can rework this, and what you will get is n by v h cube by 2 pi m kbt whole to the power 3 by 2. This is for z much less than 1. Why? Because when you have z much less than 1, look at this summation, right? F1 alpha was the summation, and for z much less than 1, that is when z is approaching 0, right? So where for z much less than 1, what happens that this z to the power by r, this will, so when you expand this summation, the higher order terms of z will simply become insignificant. Higher order terms of z will simply become insignificant, and you will have only 1 over here, okay? And so only the first term, z to the power 1, only that term will remain significant. So you can approximate f1 alpha by z, right? Because for r equal to 1, z upon 1, so it is z only, and the other higher order terms of z will simply become insignificant because z is much less than 1. So f1 alpha approximates as z, and using that, you just then do a little bit of mathematics over here. So z is e to the power minus alpha, and you get this expression. And the limiting case for this is f1 alpha max, and this, the maximum value of f1 alpha would be when alpha is 0, right? When alpha is 0, and when alpha is 0, then so if you look at this expression, this becomes 1 upon r to the power 3 by 2, right? And summation over r going from 1 to infinity. So this is an infinite series, and this value comes out to be 2.612. So you substitute this value over here, and similarly you do the calculation for the energy, right? The total energy density of the system. So you do that calculation, and what you get is that n by v comes out to be this times 2.612. So basically you've substituted this value over here and you rework this, so you get this, and this was your energy expression, right? And so you do a similar calculation over here, and finally using this expression, okay, using this expression. So this expression is unique because this value 2.612 is coming for a limiting case. And what is that limiting case? When alpha goes to 0, right? And z is e to the power minus alpha. So when alpha goes to 0, so e to the power minus 0 is e to the power minus 0 is 1. So in this limiting case, this comes out to be 2.612. And so this limiting case, when you look at, when you do again, now you so the temperature that corresponds to this limiting case, okay, when these conditions that I've mentioned over here, when these conditions are satisfied, then when you, with the temperature that corresponds to these conditions, this is called the Bose Einstein condensation temperature. So TB, again, just basically just take T on this side and work out everything else. This is the expression that you get for the Bose Einstein condensation temperature. All right. And so this is the Bose Einstein condensation temperature. Why is this temperature very significant and important? See, like I said, that when we had started our discussion, this was our condition. This needs to be greater than or equal to 1, and mu needs to be less than or equal to 0, right? Or, and similarly, when you do this, so the condition on alpha that came out was alpha is over here, when we did this. So alpha is lying between, so this was, so E, this was it. So this is e to the minus mu by kBt, right? And so this is e to the power alpha, and if this is 1, so alpha is 0, right? So from this, now, okay, just a minute. What I actually wanted to, yes. You see, when you reach that limiting value, why I said that this temperature, this Bose Einstein condensation temperature, or this critical temperature is very important. Because when you reach that limiting value of alpha, or that limiting value of Z, or that limiting value of chemical potential, then you are reaching that value when this becomes, you see, this term, my e to the power minus mu by kBt. So this term is alpha. So if alpha is 0, right, this becomes 0. For ground state, I had said that epsilon I is 0. So this energy of the ground state is 0, which means e to the power 0. So e to the power 0 means 1. So 1 minus 1 in the denominator gives you an indeterminate result. So this entire statistics breaks down at that limit of alpha going to 0. Okay, so whatever we have, so this Ni, this expression, this Bose Einstein distribution function expression, or this number of particles that are there, this expression holds good only so long as you are satisfying these conditions. But the moment you reach the limiting value of these conditions, this expression breaks down. And what happens? This is something which is very, very important. And again, after I've done this, I'll give you a brief again description about the why this result was so important and significant, and why so much of importance is given to it. So anyway, right now, so this is that temperature, this is that critical temperature. This Bose-Einstein condensation is that critical temperature. If your temperature goes below this value, if your temperature goes below this value, then the solution that we had been working on till now, that solution breaks down. So what happens? The first thing that you realize is that this expression for n that you had derived over here, number of bosons in the Bose-Einstein gas, this number of bosons is actually the number of bosons that are in the excited state. This is not the total number of bosons, because the moment you reach this limiting value that we just discussed, this limiting value, right, alpha going to 0, the moment you reach this limiting value, this number becomes 0. And the moment you cross that limiting value, that means you go to a temperature lower than the Bose-Einstein condensation temperature, you can no longer accommodate your particles in any of the higher energy states. So you are forced, see this energy that we had calculated, you can no longer accommodate these particles in any of these energy states whose formula we have calculated over here. Then your particles necessarily have to go to the ground state, which is your zero energy state. And this is what you refer to as the Bose-Einstein condensation. At the moment your temperature goes below the Bose-Einstein condensation temperature, below TB, there is a macroscopic occupation of the ground state by the bosons, as those bosons can no longer be accommodated in the higher energy states. Okay, so there is a macroscoping. It's not as if it is a gradual, okay, as you keep going down, your particles, your bosons will keep going into the ground state. No, it's not a gradual process. The moment you cross this temperature and you go below this temperature, there is a macroscopic occupation of the ground state. And that is why, if you look at the statistics, probably those of you who are in your master's course, you would be doing this, that actually this transition from T greater than TB to T less than TB, which is called as the Bose-Einstein condensation. This is a second order phase transition. There is a discontinuity in the specific heat at this phase transition. And hence, this is a second order phase transition. And because this is a second order phase transition, so, and because of this discontinuity, what happens is that the solution that was above this temperature, that solution completely breaks down. And the moment you go below this temperature, you have all the particles, all the bosons condensing into that ground state. So your expression now gets modified. So your total number of bosons, the real expression for the total number of bosons in a Bose-Einstein gas is N naught plus N, where N is what we had actually derived over here. This is actually speaking, or truly speaking, this is the number of bosons in the excited state. Typically, this represents the total number of bosons at higher temperatures. But the moment you approach this limiting value, then majority of your bosons condense into the ground state, and they are represented by this N naught, where N naught is 1 upon e to the power alpha minus 1. And so your N is given by this expression. Again, this is mathematics. I have just written the final expression. So your N is given by this expression. And this turns out to be N is T by TB to the power 3 by 2. So you can see over here, the moment your T by TB, so the moment your T becomes less than TB, there is a drastic reduction in this number N. And N naught is given as N1 minus T by TB to the power 3 by 2, right? So the moment your T goes less than TB, this becomes, this becomes less than 1, and then it's to the power 3 by 2. So as you keep going below this TB, your majority of the bosons will condense into the ground state, and N naught denotes the number of bosons or the occupation of the ground state. Okay, this is the energy. So what you see is that for the non-degenerate case, okay, so you have this solid line is coming over here, and for the non-degenerate case you simply go to here, and but actually what happens is that the moment you hit TB, your this is called your 0 point energy, and all your bosons will then have this energy only from here to 0. Okay, and this also you can see that this is T by TB, the ratio is 1, and the moment you start going below, and this is N by N naught, right? So as you keep going towards absolute 0, that is T is approaching 0, you can see that at T equal to absolute 0, this is the total number of particles, right? This is capital N, this is N naught. So N by N naught, this is 1. That means all the particles are in the ground state. All the particles are in the ground state at absolute 0 of temperature in case of a Bose Einstein gas, right? And as your temperature increases, you can see that this comes out, and as your temperature becomes this, beyond this, almost all the bosons are in the excited state. And that is why I said that when we start with the statistics, actually this is something which was very interesting. When Einstein was doing these derivations, he came to this and he realized that the solution breaks down over here, and what he predicted was that there will be a second order phase transition and the particles should condense into a ground state. But he was himself not convinced. He was himself not very much convinced about this, and in fact he gave this statistics in the year 1925, and in the year 1995, that is 70 years after Einstein gave this result, could this result be experimentally verified, and the first experimental Bose-Einstein condensation was observed in rubidium-87 and sodium-23. Anyway, so that was it. Now coming to the Fermi Dirac gas. Again, we start with the distribution function, the Fermi Dirac distribution function. Okay, here again, you know that Ni can either max be 0 or greater than 0, but greater than 0 means it can either be 0 or 1. There are just two possibilities for Ni. Either there is no particle in that particular level, or there is at the maximum one particle in that particular quantum level. Okay, and because there is a plus sign over here, so it does not matter whether this what happens to this, because even if this term goes to minus infinity, e to the power minus infinity is 0, and so this would still be and if this goes to infinity, then Ni becomes 0. So basically this term or this denominator as such has no restrictions now, and because there are no restrictions on this, so we now simply again do the same procedure. Here GS, this is something important. You see, this is an additional term that we are getting apart from what we were getting in the Bose Einstein gas, and this term comes from this is the spin degeneracy. We know that Fermi Dirac gas consists of fermions. Fermions are spin half particles. Because they are spin half particles, therefore the degeneracy associated with the spin half particles is that, I mean, you know that their spin moment is half h cross spin angular momentum, and so that half is the spin, and the degeneracy that comes is because of the spin. The degeneracy that comes is 2s plus 1. So s is half, 2 into half is 1, so 1 plus 1, 2. And that is how you get two fermions can be put in the same energy level, so long as one is in spin up state and the other is in spin down state. Okay, so each energy level, now please remember carefully, I'm talking of the energy level, but when you go to a sub level, Okay, when you go to an energy sub-level or an energy substate, then there, and if it represents your quantum state, so your quantum state, only one fermion can occupy one single quantum state. The degeneracy is in the total energy. So if you have, let's say, a number of quantum states corresponding to the same energy, then each quantum state will be occupied by one fermion. And in a state, you can have two fermions so long as one has spin up and the other has spin down. Okay, so this is your spin degeneracy that comes out. So this spin degeneracy is 2 because S is always half. So this is what you get. I mean, okay, and if it's a collection of particles, then you may have a different integral value, and accordingly, this spin degeneracy will change. But for electrons, since S is half, so for electrons, if you look at this, then this is always 2. Spin degeneracy in the case of electrons. Okay, so then again, you do this mathematics. This is all mathematics, so I'm not really going to go too much into the details of this. But finally, again, you get this similar kind of expression. Okay, and this is the same as what we had done for Einstein gas. Then you get the expression for energy. Again, you get a similar expression for energy. Now, here again, we come on to a very interesting aspect of the Fermi Dirac gas. You see, this F epsilon is called the, this is the Fermi Dirac distribution function, right? And this F epsilon, so this F epsilon is defined as N epsilon by G epsilon. If you look at this, basically Ni by Gi. So if you get this Gi over here, so Ni by Gi is 1 upon e to the power epsilon I minus mu by kBt plus 1. So this is your Fermi Dirac distribution function, which I have again written over here. What is interesting about this? At t equal to 0, okay, at t equal to 0, F epsilon is 1 so long as epsilon, that is the energy of the fermion, is less than EF at t equal to 0. And what is EF? EF is referred to as the Fermi energy. Okay, so EF is called the Fermi energy, and EF is basically so this alpha is minus mu by kBt, and this is equal to minus EFT by kBt. So basically, this chemical potential for the Fermi Dirac gas becomes this, represents this Fermi energy level. All right. So this is again something very important. Why is this important? You see, this distribution function is equal to 1 for epsilon less than EF. And I'm talking at t equal to 0. And this is equal to 0 for epsilon greater than EF. Okay. If you look at the graph, this is the graph that you get. This is F epsilon versus epsilon. So if you look at this F epsilon is 1 up to EF for all energies lying between 0 and EF, which is your Fermi energy at t equal to 0. And this becomes 0 the moment your epsilon becomes greater than EF. And this graph is valid for t equal to 0 as your t increases. Okay, so for any other t, this graph starts. So initially it will be something like this, it will go like this, and then over here it will go like this, and then so on and so forth. But what happens is that for any temperature T greater than 0 also, at T equal to this critical temperature, okay, at EFT. So for any temperature T, when your epsilon becomes equal to EFT, your F epsilon will be half, always. Look at this expression, right? So if alpha is minus EF T by kBt, so when E becomes equal to EF, then this term goes to 0. So e to the power 0 is 1. So 1 plus 1 gives you 2. So F epsilon will always be half at epsilon equal to epsilon EFT for temperatures greater than 0, and for T equal to 0, this is equal to 1 for E less than EF, and is equal to 0 for E greater than EF. What does this result actually mean? that at the absolute zero of temperature, all energy levels from the ground state up to the Fermi energy are completely filled up by the fermions, and all energy levels beyond the Fermi energy are completely empty. All right. So this is to zero. Then slowly and gradually, some of the fermions will start occupying energy levels above the Fermi energy, and at E equal to EF, the number of fermions lying below the Fermi energy and the number of fermions lying above the Fermi energy are going to be equal. So half of the fermions will lie below the Fermi energy and half of the fermions will lie above the Fermi energy for T greater than 0. Okay, so this is that result. Uh, then, this is now again, we calculate the value of the number of fermions that will lie. So at T equal to 0, what is going to be this number of fermions? And this is the Fermi energy at T equal to 0. So this is the expression of the Fermi energy. Again, what we've done is simply we've reworked this expression to get this expression. And this is the Fermi temperature. Okay, so what is the Fermi temperature? So EF0 is kBTF, right? So TF is basically, Fermi temperature is defined as the temperature which is equal to EF0 by kB. And this is what you get as the relation for the Fermi temperature, right? So these relations are important. You get a number of questions relating to these. And finally, the last topic that I wanted to discuss with you is the degeneracy in the Fermi Dirac gas for T greater than TF. All right, for T greater than TF, that is above the Fermi energy, kBT is greater than kBTF, which is equal to EF0. Alpha is greater than 0. So your energy is 3n kBT, 3 by 2n kBT, which is your same as the energy that you get from the Maxwell-Boltzmann distribution. So when it is a weakly degenerate case and your temperature is greater than that is when your temperature is greater than TF, then the Fermi Dirac gas will approximate to the Maxwell-Boltzmann gas. But what happens, which is your strong degeneracy case? So what happens at T equal to 0, at T equal to absolute 0? The energy, the ground state energy is 3NEF0 by 3 by 5 NEF0, and the pressure of the fermions is given by this relation. The other case in the strongly degenerate Fermi Dirac gas is that T is not equal to absolute 0, T is greater than 0, but is still much less than TF. Then these two relations get modified to this. The energy of the ground state becomes this, and the pressure exerted by the Fermi Dirac gas becomes this. This is at T equal to 0. Okay, so the energy of the Fermi Dirac gas becomes this, and this is the pressure of the Fermi Dirac gas. Okay, and now these are just some of the problems. In Bose Einstein condensation, the particles have strong interparticle interaction. No, the particles are non-interacting. Condense in real space. No, they condense in the momentum space. Okay, that condensation is happening in this. So when they condense into the ground state, so the ground state that I was referring to, that all the particles necessarily go into the ground state. So that ground state is the momentum space, zero momentum space. I mean, the zero momentum state is the ground space, ground state. And C, have overlapping wave functions. Yes, they have overlapping wave functions, like I mentioned to you earlier, that the thermal de Broglie wavelength, lambda thermal, becomes greater than the interparticle separation, so they have overlapping wave functions. Have large and positive chemical potential. No, again wrong. Like we saw that the chemical potential is negative and its limiting value is 0. So it will never have positive or large values. Okay. For a black body radiation in a cavity, photons are created and annihilated freely as a result of emission and absorption by the walls of the cavity. This is because the chemical potential of the photons is 0. Yes, because the chemical potential of the photons is 0, so any number of photons can be created or annihilated, and there is no conservation on the number of photons that are there in the system. Photons obey Pauli's exclusion principle, absolutely wrong. Photons are spin 1 particles, so they do not obey Pauli's exclusion principle. Photons are spin -1 particles, again no, they are spin 1 particles. The entropy of the photons is very large, no. Okay, uh, then this is another question. A large number n of ideal bosons, each of mass m, are trapped in a 3-dimensional potential this. The bosonic system is kept at temperature T, which is much lower than the Bose Einstein condensation temperature, Tc. The chemical potential satisfies. Now, please remember what I had said, because you are considering a bosonic system, your temperature T is much less than Tc. So what is the condition? Your chemical potential, if this is a harmonic oscillator potential, right? So since this is a harmonic oscillator potential, therefore your mu will typically be less than the ground state harmonic. So you know that the energies of the harmonic oscillator kaise aati hai? The in a quantum harmonic oscillator, n plus half h cross omega. So the ground state will be n equal to 0, so half h cross omega. And if it's a 3-dimensional case, then 3 by 3 degrees of freedom, so 3 by 2 h cross omega. So your mu will be less than this, right? Because this is your ground state energy. So A is the correct answer. Okay. At temperature T Kelvin, the value of the Fermi function at an energy 0.5 electron volt above the Fermi energy is this. Then T to the nearest integer is, so KB value is given in terms of the electron volt per Kelvin. So you know that the Fermi distribution function is given by this. So T is equal to E minus, now we just rework, so T is, we are now using the reworking this. So you do this calculation so that your this T comes over here and everything else comes over here. So you get this expression. Now it says that the value of the Fermi function at an energy 0.5 electron volts above the Fermi energy, right? So E minus EF is 0.5 and 1 minus Fe. So above the Fermi energy, so the value of the Fermi function. So Fe is equal to 0.01. Fe is equal to 0.01. So 1 minus Fe is 0.99. And then KB ki value, we just put this over here. So you get 1262.3 Kelvin. So 1262 Kelvin is the answer. Okay, so that is it. Thank you so much for giving me such a patient hearing. And I hope that whatever sessions I've taken, people have found those sessions to be useful. And I also hope that, yes, and definitely if there are any questions or if there are any queries, you can send it to me. That's why I specifically given my email ID also. I'll try to answer those questions. You can also send it to Punita ma'am. I'll see if I can, or Pushpa ma'am, they'll forward it to me, and I'll, whatever best I can provide the solutions, I'll definitely try to do that. And yes, if there are any questions, ma'am, should I be taking these question answer box?
It's all up to you. I see the attendees are decreasing because, sitting continuously for 3 hours, 15 minutes
Yes, ma'am.
for
Yes,
the students is also a bit too much of a work. So what I will do is I will forward it to you. You type out the answers. Some of them I will type out, we'll forward it to them. If their name is there, then they can get all the answers.
Right.
If somebody is anonymous attendee, then I promise them I will not answer that question. They have to identify. If they ask me what is the difference between identical and distinguishable. So I said, you are not identical, please be distinguishable. So the statistical mechanics is everywhere. You have beautifully, in a concise manner, covered entire formulae list as well as, revising of what are the aspects of statistical mechanics going from classical to Bose Einstein. So I don't know whether the students are able to understand this, that there is one speaker like you who is covering all the entire physics field of statistical mechanics with its formulae and concepts, touching them and touching the numericals, and I am going slowly covering the entire base the way we do in a classroom. So all coupled together should lead to a very good understanding. for the subject, and we'll try to do this for all the subjects, not just one. So thank you so much, Dr. Aditya, and students, your questions will be answered within a day or so. Don't worry about it. Okay, Dr. Aditya, I would
Thank you so much.
Thank you very much.
Okay.
Thank
Thank
you.
you, ma'am. Thank you, Pushpa, ma'am.
So, Dr. Neetu, I request you to stop the recording for today. And